Well, let's get started. Good morning or good afternoon, depending on where you are. My name's Steve Gordon, and I am the head of the Outreach Committee for the SIG HPC Education Chapter. And today we have Alan O'Case and Kenneth Host to talk about EESSI, and I'll let them introduce themselves and the subject in more detail. So, Kenneth, are you going? Go ahead, please.
Yeah, I think Alan will start.
Okay.
Will you share your screen there, Kenneth, and then
Oh,
we
right.
can.
Yes, that's an important detail. There we go.
Okay, so yeah, I'm going to introduce so the way we pronounce it actually is easy, and that's what we managed to come up with here. So it's the European Environment for Scientific Software Installations. We tried to give the title a little bit of a punchy feel, so try and draw some parallels with the subscription service you might have for your TV. So the idea is that we want to create a software environment that is production quality of high standard, reliable, optimized, works on lots of platforms, and you only stream it. So you stream exactly what you need from the stack. That's basically what we want to do. And then to introduce ourselves. So Kenneth is he's an HPC sysadmin at Ghent University. He's been there for quite a few years now. He contributes to a number of different open source projects, but probably the one he's most well known for is EasyBuild, where he's the benevolent dictator. And he's also been, so we've been working on EC without funding or silently for the last couple of years. And so he's been there since the beginning and an active contributor to that. And we're now in the space where we are funded. So through the multi-X scale, which is a Euro HPC Center of Excellence. And I'll talk a little bit more about that later on. So for myself, I'm currently a research software engineer with CCAM, which is a organization that promotes the use of advanced computational methods, particularly in materials modeling and biophysics and lots of different areas actually. And it's been around for about 50 years, or even more actually, and has a nodal structure. So I'm situated at the University of Barcelona in Spain as a node within that network. And so more than 10 years experience of working and leading on EU-funded HPC projects, and multi-X scale is the newest one for me, and I'm the technical manager within that project. So for the first part of the talk, Kenneth's going to take over and walk you through exactly what EC is, what problem it tries to address, and how it goes about doing that. And then I'll take over later on to talk about more about specific education-related things.
Okay, thank you, Alan. So first of all, the context here of the EASY project is getting scientific software installed. So this is maybe surprisingly difficult. Scientific software is its own type of thing. It's not your regular software package that you install with a package manager like Yum or whatever equivalent you have for your favorite operating system. It comes with a whole bunch of caveats. So usually this software is installed from source to really optimize for the hardware you're going to run on. It's developed by scientists, which are sometimes not trained to develop software, and you can tell based on various aspects of the software. So that's already a problem and has been a problem for a long time. But this issue is actually getting worse and getting worse fast for a number of reasons. The scope or the the variety of computational science software is expanding. So we see this growing quite rapidly. Bioinformatics was a good example until a couple of years ago, but definitely AI and ML more recently are taking the crown here in terms of new software projects that are popping up, new techniques that people are using in their research and so on. Along with that, we also see a bit less experience in scientists whenever they're maybe only using this type of software, but also developing it themselves. So it looks like people are less well trained for this to get it working, let alone to optimize it and have a good installation of that software. On top of that, and somewhat related to that, there's an explosion of open source scientific software, not only because of more domains, but also because of a push towards more open science. So people publish papers, and publishers expect the code that was used for that paper to go along with it. So you will find things in GitHub repositories, which means other people will pick up on it and want to get it to work. So you basically have a big increase in the number of different tools that are available as well. Along with this, there's a big increasing variety in hardware as well. So we're coming from an era where Intel was king, and anything else didn't really matter too much. There were some exceptions, but it was mostly Intel all across the board. That is changing quickly. AMD is back. ARM is very relevant already in HPC. Power is still there a little bit, although that definitely looks like a dead end. But in the near future, we're also seeing RISC-V type CPUs and systems, HPC systems coming relatively soon. Next to that, we have accelerators, the NVIDIA GPUs, which have been around for a long time, but now AMD and Intel are also in that space and providing this special purpose hardware. There's also the rise of the cloud. So researchers are maybe not happy anymore with only on-prem hardware, but they want the flexibility of the cloud, regardless of whether that's going to cost them more. It's very easy to scale up, scale down. It's there whenever you need it. But how do you get your software running on there? How do you get it running well? Is not a solved problem. Sorry. And of course, in contrast with all of this is the available manpower in support teams. So these teams are expected to somehow keep up with this increase in software and this wide variety in hardware. And of course, that's a problem that's only getting worse. So this is really the motivation for the EESSI project. So EESSI stands for the European Environment for Scientific Software Installations. And you can probably notice that we gamed that a little bit so we can pronounce it as EESSI. It's really a shared repository of optimized scientific software. And one thing very particular here is that we share the installations themselves. So we don't share recipes. You can build and install that software. It's really the installation itself. And it's also not traditional packages like you get with Yum or Debian packages. So it's not the package you can install. It's really the software is already there and is streamed, like Alan said. And we'll give an idea of what that means during the demo halfway through the talk. We have a lot of goals with the EESSI project: avoiding duplicate work, providing a uniform software stack for users, regardless of the system they use. So whether they're using their own workstation, laptop, whether they're using the cloud or using an HPC system, they should be able to use the exact same software environment on all these systems. So they should always land in a familiar environment and basically be able to focus on the research they want to do rather than getting things to work. There's several things we focus on in the project. Performance is a big one because we're playing with computational science software and these big fancy systems that cost a lot of money and that you want to get the most out of. Automation, because that's almost a necessary evil because of the amount of software that we deal with and the variety of hardware that we deal with. We want to do a very good job at testing the software that we provide. We want to collaborate together and help out each other to get rid of some of this burden. The performance aspect here is very important and is something that I see people glance over maybe a bit too easy. So the software that you're running should be optimized for the system that you will run it on. And then I don't mean the code that you're running, but actually how the software was compiled, how it was built. It should be targeted towards the CPUs that you're going to run on. And the impact of this can be quite significant. So this graph shows a little experiment that we did a while ago with GROMACS, where we're running the same version of GROMACS, so exactly the same code, but built in different ways. So built with different compiler options or different options to the configuration command that configures the build. And the main difference here is the instructions that are being used by these GROMACS binaries. So if you install a GROMACS with Yum, you'll get an older version as well, but you'll get what we call a generic binary. So something that's not optimized at all for a particular CPU. So that's the gray bar on the left. So then you get some kind of performance. This says 1.09 simulated nanoseconds per day. So that's a measure of how fast the simulation goes. But if you look at using a more optimized binary that uses the specialized vector instructions like AVX, AVX2, AVX512, you see the performance going up. And the difference is quite big. So compared to using a generic binary and one that's properly optimized for the CPU you're going to run on, there's a 70% speed up in the simulation. So that's quite significant. So if you're not careful how you're installing the software or how you're building the software, you may be paying for that quite substantially in performance. And that's something we want to highlight because most people say, okay, there will be a difference, but maybe it's not going to be that big. It could actually be very big. And we see this not only for Chromax, but for lots of scientific software. Some of the major goals we have with EESSI are avoiding duplicate work, not only for the researchers in trying to get their software running, but only for HPC support teams, which typically install or provide a software stack for their researchers. There's already a big improvement there in recent years where people start using tools like EasyBuild, but also SPAC to automate the installation process of scientific software. But we see that this is not enough, or not enough anymore, at least. So even when using these tools, you will sometimes still run into trouble when something is not working the way you expect it to, either because of peculiarities of the system that you're using that you're doing that installation on, or because maybe the sources disappeared upstream, and then EasyBuild usually downloads the sources for you, but if it can't, then you'll have to go ahead and fix that yourself before it can continue. So with these tools, we're sharing build recipes, but we think it's time for the next step and really working together on the software stack itself and having something that's shared in a way that it works everywhere. The uniform software stack is then the result of that. So you'll get a software environment that is basically exactly the same everywhere, no matter the system you're running on, no matter which Linux version or operating system you're using. And we think we can do this in a way that we're not sacrificing performance while doing that. So sometimes we often see when people use containers or Conda, is that they're maybe without realizing it running generic binaries. And as we've shown in the graph, you can pay for this big time in terms of performance. That's something we definitely don't want to do. And this enables a bunch of use cases like facilitating HPC training. If we can give people a software stack very easily, and that's the same on a variety of systems, they can get trained on that software stack and then use that software stack when they go back home. And there's a couple of things there that Alan will cover as well, so I won't go into much detail here. All right, so that sounds all great, but how do we actually do this? So what do we need? We need a way to distribute software globally. There's different ways of doing that. Packages, the traditional packages is one way, but that's, we think, not enough or not easy enough to get started. We need some kind of abstraction from the operating system. So whether you're running Ubuntu or Fedora or some other RHEL derivative, it shouldn't really matter too much. So the software we provide should be usable on each of these systems. So sort of like a container, but maybe in a different way. We provide optimized builds for different types of hardware, different types of CPUs. And ideally, the end user doesn't actually know which software installation they have to use depending on the hardware that they're on. So some kind of auto detection mechanism and something that's intelligent and picks the right installations for your hardware automatically would be really nice. And we can actually provide all four of these things with the EESSI project by leveraging different open source projects. And I'll explain these in the next couple of slides. So zooming in a bit on the EESSI project, this is the high-level overview. We basically have three layers: a file system layer, a compatibility layer, and a software layer, which each tackle one of these bullet points in the previous slide. So there's a lot going on here, lots of technical details as well. But what we're really doing is with the file system layer, we're distributing the software that we provide. That software is built on top of a compatibility layer, which basically levels the ground across different operating systems. So no matter which Linux version you're using, we don't really care because we're not going to use most of it. We will use our own glibc in the compatibility layer, for example, and build all our software against that glibc. So we're in full control, which is somewhat similar to what containers do. And then on top of that, we're going to have the optimized applications and all their dependencies. Optimized in the sense that they are built separately for old generations of Intel, new generations of Intel, different generations of AMD CPUs, ARM CPUs, and so on. So you basically get the same software multiple times, but optimized for different hardware in the software layer. For testing all of this, we're looking at Reframe as a testing tool. And And yeah, like I said, there's a lot going on here, but I'll try to zoom in on some of these aspects, and so you get some feeling of how this works. So the file system layer first, for here we're using CERN VMFS, which is a special file system that's implemented by CERN. They've been using this for over a decade for distributing the software that they use for the Large Hadron Collider project, for example. And it's really a network of servers in some sense, where there's a central server that has the main copy of the software in some sense. So this is also where you add new software. Then there's mirror servers, the Stratum 1s around that basically have a full copy of everything that the Stratum 0 has. But these are read-only, so you don't get to add anything to the software here. That only happens centrally, and it just tapers out through all these mirror servers. And then as a client, so whether you're in the cloud or you're on your laptop or you're on an HPC cluster, you're basically accessing the software stack by talking through one of these mirror servers. And all of this happens transparently. So as an end user, you don't really know that this whole network of servers is behind that. You're basically just trying to use files, and whenever you're trying to use that file, it's being downloaded in the background for you as you try using it. So in some sense, it's similar to Netflix. You can pick any movie, but the moment you actually start watching a movie, that's when it's being downloaded onto your system while you're watching it, while you're using it. So in that aspect, it's very similar to that. But the end user is totally oblivious to what's going on in the background. So it looks like the software is there locally, but it's really not. The compatibility layer is how we level the ground across the different types of operating systems we want to support. For now, we're only looking at Linux, and that's been working quite well. We know there's a way to also do this for macOS, but then yeah, that's different enough that we need to redo a whole bunch of things, which we haven't looked into yet. But then, technically speaking, it is possible to also support macOS. For Windows systems, we're looking at the Windows subsystem for Linux, so basically an Ubuntu container that you can easily run in your Windows system, and you're basically in a Linux environment. So it also works in there. So that's just another Linux distribution as far as we're concerned. What we're doing here is building our own small Linux environment, glibc and a bunch of libraries next to that. So stuff you typically find in your operating system. But we're doing that ourselves because then we know what we're actually building against. So whether your glibc in your OS is old or new, we don't care because we're not going to use it. So we have one fork or one subdirectory here for the different CPU types we support, one for ARM, one for Power, one for x86. So these are not optimized installations for specific types of CPU. We just have one of these for the different CPU families. And I'll show a bit in more detail during the demo what that actually involves exactly. So this is, yeah, let's say the middle layer. This is where the magic happens, where we can provide software installations that work on a variety of operating systems. And then on top of that, we have the software layer, which is the actual scientific software that the researchers care about. This is optimized for specific CPUs. Today, we're installing these with EasyBuild, but we could use any tool, really. What we're doing here is not specific to EasyBuild at all. These applications, this scientific software is built on top of the compatibility layer. So we don't use anything from the host OS, at least if we can avoid it. There are some exceptions like GPU drivers and things that have to come from the OS. But yeah, we can bridge that by adding libraries in the compatibility layer to make sure that works. We're using LMOD as our modules tool to provide access to those installations. And a nice detail, which you'll see pop up in the demo, is the ArchSpec library, which can detect what type of CPU you have, down to, is it an Intel Haswell, is it an Intel Skylake, is it an AMD Rome? So beyond just x86, it knows what type of CPU you have, and based on that, we will pick the right part of the software layer that's optimized for that CPU. There's a fallback mechanism as well. So if you have a brand new Ice Lake, for example, which we don't have optimized installations for yet, it's smart enough that it knows, okay, you have an Ice Lake, there's only Skylake provided. We'll just fall back to Skylake because that's the best possible match for your CPU. So it's even if there's no exact match, it's intelligent. Testing is a big aspect of the project as well. This has been lots of ideas floating around here. We have a test suite repository. It's not really big yet. I think we only have a GROMACS test in there now. But we're trying to come up with a test suite that works regardless of the system it's being run on. The fact that we have a shared software environment, of course, makes it a lot easier. So we know what type of software we provide. We know what the module names are, how to load that software, which versions it is. So that's the same across the different clusters or even workstations. But we're still trying to figure out how do you make sure it works regardless of whether you have 2 cores or 100 cores. So things like this we're still working out. We're looking at Reframe there as the testing tool to drive all of this. And that's definitely a big aspect of the project as well. And we're looking at not only testing functionality, so is the software installation correct? Does it produce correct results? But also at performance and scaling. So is it fast enough, or is the performance that we're getting correct, or is it 10 times slower than it could be given the hardware that it's being run on? So that and scaling across multiple nodes. So we'll be looking at things like this as well. This is early days for this aspect, but we have some interesting ideas there. One thing we already did do for testing is a scalability test of GROMACS, which is covered in detail in the open access paper we have, which is available at the link here. So what we did here is run GROMACS on a system at the Jülich Supercomputing Center, a big cluster. We scaled it up to 16,000 cores, and we're running different binaries, different GROMACS binaries. The red one in the middle is the GROMACS installation that comes with the system, so that the system administrators or the support team provided for the researchers. So that's properly optimized for the hardware and the network of Yusuf. The black one is what we provide in EESSI. That's the optimized installation for this for the CPUs in the Yusuf cluster. So that's AMD Rome. And the blue one is then our generic fallback installation, which is not optimized at all. And what you can see is, of course, the non-optimized version is a bit slower than the optimized one. But if you look at the black and the red dots, our installation seems to be a bit faster than the system installation. Now, it's in the noise, sort of, but that does tell us we're scaling very well, and we're scaling as well as the system installation does. So that's very encouraging. And that basically means that it looks like it is possible to get very good scaling, even though you're using an installation that is not specifically built for this particular system. So that's a very important result. And all the details are in the paper there, what's going on exactly. So the current status of the project, we've been working, like Alan said, for this a couple of years, actually, right when the pandemic happened, like 2 weeks before. We had, in some sense, a kickoff meeting, or really a meeting where the idea emerged to do something, to work on something together like this. And the side plan there was also to have lots of beers with each other, plan lots of meetings, and have some fun. But then, the pandemic happened, and we actually had to do some work, and we did. So pretty early, I think after about 6 months after spinning the idea, we had a working proof of concept with a couple of software packages like GROMACS, like OpenFOAM, like TensorFlow. And we could start playing with this on different systems and see, okay, we know how to build this, we know how this works, and how this needs to be done. Now, this is, of course, was not a production setup, so that's our next big goal, to getting this working in a way that it's stable and reliable, and that we can add lots more software to this and see whether this is actually being picked up. We do already support a different bunch of hardware targets, different Intel and AMD CPUs, ARM CPUs that are in the AWS cloud, and also still power, but we're stepping away from that because it's too painful to keep it supported. In this effort, we've been getting some help from both Azure and AWS. Of course, for the cloud providers, having a software stack that works well, almost automatically or magically, for researchers, it would be very welcome, because people can spin up VMs, but if they can't get their software working on that, they won't get very far. So they have seen or they have expressed their interest in this project and have been helping us out by basically letting us use their cloud for free to do these builds, to do these tests, and to have working demos and things like this. So they've been very supportive of the project. That helps, but that doesn't mean there's manpower to actually get things working fully. So we've looked for dedicated funding, and we have that now through the multi-xScale Euro HPC Center of Excellence, and Alan will briefly cover what that's about. There's also lots of ongoing effort in the project. So we have this working proof of concept, and that's very good. But we're now taking the necessary steps to be really taken seriously and to let people rely on this. So one thing is building a bot to automate the workflow of adding software to EESSI. So because we support different types of CPUs, different generations of CPUs, now about a dozen or so, it's in some sense painful to add software to it because we have to build it for all these different types of CPUs. So we're basically automating that whole process, and we're working towards a way that people can send a pull request to a GitHub repository to say, I want to add TensorFlow 2.8 into the EESSI repository. They open the pull request, and then a bot kicks off, does all those builds, or at least tries to do all those builds, see if they work. And if they work, then a human can click, OK, let's deploy it. And it gets added into the EESSI repository. So it's basically automating to the point where it makes sense. We want to make sure that nobody can just push random software into the repository. So there's some kind of review process there as well. But we don't have humans triggering manual builds or compiling stuff by hand on a dozen types of CPUs. So that's something we want to have fully automated. That's an important aspect. Another one is support for GPUs. So supporting different types of CPUs is not a big problem. Supporting GPUs, and especially NVIDIA GPUs, is a bit more painful because there's the aspect of the GPU driver. So there we need to rely on something that's in the host, because we can't ship GPU drivers in the compatibility layer, that they're too much tied to the kernel and what type of CPUs you have. So that has to come from the OS. So we need to bridge that somehow. And also the CUDA license. So CUDA is not open source software. So just providing it in a publicly accessible software stack is not allowed. You can strip down the installation to only the runtime part. So that is allowed. And then we have to make sure and the necessary gaps are filled so things can actually work. But from a technical point of view, this is a bit more difficult. But yeah, it's very important. To be taken seriously, of course. And next to that, there's lots of other activities towards making EESSI stable and reliable. Hopefully, we can get to that in the next couple of months. There's lots more details here in the presentations that were recorded from our EESSI community meeting last September. So if you're wondering about the ongoing efforts, you should take a look at the link at the bottom of the slide here. All right, and then Alan can briefly cover the multi-xScale project.
Yeah, so while Kenneth is just getting ready with the demo, I can just give you a couple of points on this project that's kind of funding EESSI at the moment. So it's Euro HPC Center of Excellence. There's been centers of excellence in HPC in Europe for about 6 or 7 years now. So I used to work on one of those for quite a while. And so this is one of the new batch that's funded through Euro HPC. I'll talk about that after the demo a little bit more. The budget of the project overall is about 6 million euros. 50% of that comes directly from the EU, and 50% is co-funded by the national authorities of the partners. And of that entire budget, then about 50% is just for EESSI related activities. So in general, the collaboration is between EESSI and kind of my employer, CCAM, so this network of scientists across Europe, which has this nodal structure. The total number of partners is 16. EESSI is basically taking care of all the technical stuff, kind of along the lines of what you've seen so far. And then the CCAM network is the one that provides the scientific expertise. So the driver really for that project is 3 scientific showcases. They're multi-scale the idea is to enable multi-scale simulations and targeting 3 different areas. So one of those is helicopter design and specifically certification to speed up certification for civil transport. The other one is battery applications and looking forward, right, to increasing battery capacity and energy density and talking about the sustainable energy transition. And then the last one is ultrasound, to be able to use that more for non-invasive diagnostics and for other biomedical applications as well. And so that's basically multi-scaled in a very, very concise nutshell. So I think Kenneth now is just going to give you a demo of how you spin up and use EESSI in a couple of different environments.
Yep. Okay, so before I do that, let me check if this is still active here. Yeah, it hasn't died on me yet. That's good. Okay. So what I'll do is I'll give a quick demo of EESSI in two different scenarios. So one of them is starting from scratch, really. So spinning up a Ubuntu VM in AWS, and it happens to be one on an ARM Graviton 2 CPU, where we don't have anything installed yet. So we're basically getting a bare OS, and we want to see what we can do and how quickly we can get something running there. So we'll need admin privileges for this, because we will need to install certain VMFS, so we get access to the EESSI software, the EESSI file system layer that provides the software. So there's all of this is not available yet, but I'll show you how to install that, and it only takes really 2 minutes. And that's also the only thing you need to do to get access to all the software that EESSI provides. And then we can set up our environment and start running scientific workloads. That's one example. I'll kick off the installation part of that in here. So this is, you'll have to trust me that this is an empty Ubuntu VM. We haven't done anything here other than spin it up. So I'll start with cloning a GitHub repository here that has a script that I can run. Okay, so that's our EESSI demo repository. The link for that is in the slides as well. This has a script. This one install CVMFS EESSI Ubuntu. Ubuntu with a capital U. Okay, so this script has a bunch of commands in it, and it really does three things. So it starts with installing CVMFS. So it downloads that from the CVMFS maintainers, essentially. It then downloads a small package that contains the EESSI configuration for CVMFS, and it installs that. We do a minimal amount of configuration for CVMFS. This basically means the important thing here is use a 10 gigabyte cache for downloading stuff. So yeah, we're giving CVMFS that amount of space and not more. And then we do a setup, so the EESSI repository will be available. So I'll just start running the script. This will take about 2 minutes. And then I'll swap over to the other demo and then come back to this later. The other demo is using EESSI on an HPC cluster. And in this case, it's a RHEL 86 cluster with AMD Rome CPUs. In here, we're a bit more lucky because EESSI is already readily available. So I can just hit the ground running here and start using the software that's in here. So what I'll do, that should be here. So this is one of the HPC Ghent systems we have at Ghent University. And I want to run the GROMACS job. What I'll do is I'll submit this job script, which is a Slurm job script asking for 12 cores to run an EESSI demo with GROMACS. And the first thing I do before starting to use any software is to source the EESSI init script. This will set up the environment to start running software with EESSI. And I'll show interactively what that actually does on the Ubuntu system. Once that is done, we can load a GROMACS module that is provided by EESSI. This part is about downloading an input file if it's not there yet. And then we can start running GROMACS and tell it to use the 12 cores that are available. So I'll just submit this with SBatch, and that should start running straight away. Yeah, because it's running in a reservation. And I'll get back to the output of that. Well, we can actually check. It should be showing the output quite quickly like this. And here you can see that GROMACS is actually already running and using the 12 threads. So this is not a GROMACS on the system. It's a GROMACS that comes from the EESSI repository that's mounted through CVMFS. You can see here which binary it's using. And it also did the auto detection. So, and I didn't actually tell it anywhere that it should be using the AMD Rome or AMD Zen 2 optimized installation of GROMACS. It did an auto detection for that. So you can see that's actually happening here. So that just works. And any user can do this as long as EESSI was configured essentially by the HPC system administrators. And that's one of the end goals we have as well, to get EESSI on as much systems as possible. Okay, here we can go back to the Ubuntu system. So now the installation is done. The install script has completed. And all this basically means is that now we have this EESSI repository available, eesyhpc.org. This is auto-mounted, so if you do an ls, it may be a bit sluggish before it responds. And any files we access in here will be basically downloaded on the fly when we are accessing them. To show this, so the installation is complete. Now I can source the init script that's included in the repository. So this init script, I can do a source, and you will tell that we use ArchSpec to do the CPU detection. So it knows this is an ARM CPU, a Graviton 2 ARM CPU, which means it will be using this part of the software stack, which is optimized for ARM Graviton 2. It sets up the environment for doing that. It picks up the right LMOD configuration file and so on. And now we're ready to go, which means we have GROMACS, TensorFlow, OpenFOAM. All of these we now have available as a part of the EESSI repository. And to show that this actually works, I can run any of these demos: GROMACS, OpenFOAM, TensorFlow, Bioconductor. So these are R packages for bioinformatics. Let's do the Bioconductor run. This has a run script, which is quite short. It just loads the module, so it assumes it's already there. That means you have to do the init script, the sourcing of the EESSI init script first, and then it just runs a small R program that's included in this directory here. And when I do that, you'll see that it takes a while to start up because it's basically pulling in that software in the background for you. But once it's there, it starts running and starts producing the output that corresponds to the R script. So we've basically only installed CVMFS. We've installed the tiny configuration file that tells CVMFS where the EESSI repository is, and we're good to go. We can start doing our science. And of course, all the software that's available in here should work fine. So that's, yeah, both on Ubuntu, Ubuntu ARM system and a RHEL 8 AMD Rome system. And of course, any varieties of these, it basically just works. So that's the idea. The next couple of slides outline that step by step. So I won't go through these because that's basically what I covered in the demo, but you can see the installation instructions essentially fit on a slide. So it could hardly be any easier than that. If you're lucky and EESSI is already available on your system, you can just start using it as a regular user. You don't need any admin privileges or any special software. You just source the init script and you're ready to go. If you want to try this yourself, we have what we call our EESSI client container. So you need CVMFS to get access to EESSI currently. And convincing your sysadmins to install it just to play with it may be a bit difficult. But in this container, we have CVMFS available itself. So it's really a bare bones container. I think it's CentOS 7 still. Yeah, it says it here, CentOS 7, which has the CVMFS package installed and the EESSI configuration file installed. And that's all you need. And by doing some magic here with this fuse mount option that both Singularity and Aptainer support, we can actually mount the EESSI repository while the container is starting up. So that means as all you need is Aptainer or Singularity. You don't need any admin privileges. So if you have this on any system, any HPC system, this should work. So you just start a shell in this container, you source the init script like I was doing before, and you should see it setting up the environment, and you can start running GROMACS, OpenFOAM, TensorFlow, or anything that's included in EESSI. Okay, that's the demo part. So I'll pass the word back to Alan. We're going to do a screen share switch here. So Alan can drive the slides.
Okay, so you can see that now, right? That's okay. Yeah. So Kenneth is kind of showing you what EESSI is what it can do, what it's about. So I want to talk about the context for education a little bit more and what potentially the impact could be there. So to do that, I want to give you first a bit of the European context a little bit, because that's where Kenneth and I are located and that's where our project is funded. So we're within the Euro HPC joint undertaking. That's the idea there is to develop a pan-European supercomputing infrastructure, including two machines in the top 5 of the top 500 sometime before 2027, right? So exact dates I don't know, but that's the goal at least. To support research and innovation activities on these systems, the idea is to develop an ecosystem around them, right? So to provide the resources and then develop the ecosystem as well. And ultimately, one of the things that they want to do in Europe is to simulate the technology supply industry. So probably there's this feeling in general that there's an over-reliance on external parties for technology within Europe, and that something needs to be done to encourage and enhance and grow the technology supply industry within Europe itself. And that's why we see this move also towards RISC-V and things like that, and so much of a push in that direction. So, and the other thing is that they want to make these resources available to a large number of public and private users, right? That doesn't just mean academics, it also means like public as in public services, and also like small and medium enterprises. So the budget in the past, between 2018 and 2020, it was 1.1 billion. Between 2021 and 2027, it's going to be around 7 billion, and that may even be increased. And the expectation is in the end that you will have a lot of resources, and they'll be open to everybody, but the access itself will be competitive, right? So that people will have to compete for time on these resources. There are 32 signatories, so 32 Euro HPC countries. And you can kind of, it's fair to probably assume that those that have a culture of HPC, so those who have like, supported HPC over the last 20, 30 years and have run large HPC centers, they're probably going to have an implicit advantage in this competitive process, right? Because of their experience in the space. The other part of the context that I wanted to talk to you about was the education and training in Europe. So basically, I just want to briefly highlight this report that came out in 2018. That was basically listing all the courses. It uses an AI methodology to figure out and to scour the web basically and figure out all of the academic offers that were available within the EU in 3 different areas, in AI, in HPC, and in cybersecurity as well. So I'm not interested here in the numbers that they show, but they basically, found a list of numbers for bachelor and masters and just put those numbers together. What was interesting for me, at least at the time of the report, that's 2018, or when it was published a little bit later, was what was happening at the time, right? So Brexit that was basically all of that time was when Brexit was being discussed, and in 2020 was when the UK left the EU. That report was interesting because I came away from it thinking, is the EU walking into an education and training crisis, right? Because in that report, the UK had 62% of all the EU HPC training programs, and they were leaving the EU, right? So this is seemingly a big deal. Now, there's a caveat to that, and the caveat is that the AI methodology, and it was acknowledged by them, is that was heavily focused on, or heavily biased towards English language courses. So this may not be entirely representative. Nevertheless, it was alarming, right? So the thing about education and training is that in some ways, spending money on hardware is kind of easy, right? I mean, in the sense that you decide how much you're going to spend, and there's a tender process, and somebody agrees to offer you hardware for that amount of money, and that lifetime of that investment is about 5 years. But the thing is, it's a lot of money, right? And bootstrapping that investment so that you see an impact in the IP that's generated within your community, and the uptake from SMEs, and probably also from governments as well. And that's really hard, because that requires a lot of people, right? Not hardware, but people who are able to leverage it, who are able to improve it, contribute to it, and enhance these infrastructures, right? But you don't want to import that expertise, or at least it's not a sustainable thing to do. It's not a desirable thing to do. And also you have to consider, for the EU at least, you have to consider the internal brain drain as well, right? So from strong countries who have like experience and a lot of financial investment in this space, that they don't suck up all all the useful talent from smaller countries who don't have that much of a footprint in the space. And so one of the things that's really needed is like a way to identify the talent, to develop that talent, and that's what I want to talk about now, and also integrate that talent, have a pipeline to do that, right, into the ecosystem that they're trying to develop. So one of the things I think that's really important when you think about that is that any training we do in HPC, if we're talking about Euro HPC, it has to be inherently scalable, right? So I feel in general that HPC should not be considered to be for elite people, right? It should be it's in everyone's interest that it's just a tool, right? It's a tool for scientists, and it should be open to all scientists, whether they be in academia or industry or wherever. The specific case of Euro HPC, that's 32 countries, right? And in those 32 countries, there's thousands of third level institutions and more than 500 million people, right? So everything you do in that space is going to have to be inherently scalable. But there are a lot of challenges here, right? So if you want to cast such a wide net, you have lots of technical challenges, right? So things like connectivity, like the hardware infrastructure that you will need to provide these training courses, the software infrastructure, which, you know, we're making a connection here where EESSI could help provide that, but also the configuration of all these things together, right, to make it all work very well. There's the technical thing, and then there's also pedagogical as well, right? So we need education materials, we need the instructors to teach them, and they're probably going to have to be in many different languages as well, right? So the only thing I'm really going to talk about here is the software infrastructure, but you can see there are many issues that really need to be addressed to make this really scalable. So pet interest of mine, and one of the things that is really interesting is this idea of using cloud-based clusters as scalable resources. So the issue that I have with real systems from my experience in a number of different sites is that they typically come with very strict security requirements of people. And that usually means for an instructor or a learner, there's a lot of bureaucracy that they have to deal with. And for a learner, especially somebody who's at the beginning of their learning journey, these can be very intimidating, right, and off-putting, right, as regards to HPC. It gives that impression of, for me, I feel it gives the impression of being a little bit elitist, right? They're introducing this barrier that sometimes is hard for people to surpass before they even get started. And the other thing about from a practical sense, right, if you're running a large HPC center, you have to think, would you really consider running training courses for arbitrary institutions and companies from across the EU on your production system? Not really, right? Because you have an obligation to your users who are there, right? So you make certain level of promises about that you're going to maintain their data, that people in general are going to be good citizens and not like slow down the system or something like that, which is a frequent thing that happens with beginners who are not familiar with the idea of a shared resource. So that's probably not something that you're going to do in general. And so typically what that means is you end up having a training system for people, which is not necessarily the same as the production system, right? Slightly different in some ways. So either way, that you're already starting to make sacrifices, right, for this idea of being able to provide training courses. The good thing about cloud-based clusters is that they're unencumbered, right? You can bring them up, you can take them down, and you can throw them away. And you're not relying on them. They're not your production resource. They're only there for some period of time. And with the people who use that resource, you can agree with them in advance that they shouldn't consider anything there to be secure. They shouldn't use it as a production system. They shouldn't store their data there long term. And it's just a training resource. And they don't necessarily have to be toys. So what we've done in EESSI is we've successfully tested EESSI with the InfiniBand fabric that you can get in Azure and the EFA fabric that you get in AWS. So you can have a fully functioning, like as good as the hardware can give, version of MPI, so you can have multi-node systems and everything, and all of that will work. They can also be configured to run with scalable file systems. So, for example, if you're going to do it yourself, it would be something like Lustre, but there are also commercial offerings from Azure, from all of the big providers, right, that you can also use in this space for a scalable file system. And because they're cloud-based clusters, they can be made to be reproducible, right, depending on the tool that you use to deploy them. And in this case, for me, reproducible means scalable, right? So you can consider the idea of having clusters that are even just event specific, that are only for a particular training course, and then they will be destroyed. So this is something that becomes possible. And for me personally, I contribute to a tool called Magic Castle. That's a deployment tool that comes out of Compute Canada. And in that, there's a lot of additional features, and you can add new ones, right? But the features that are already there are things like Jupyter Hub, or Studio, VS Code. You can do visualization on these things. So they can be fully capable systems, right? We can do a lot of training content. So how does EESSI facilitate this HPC training? Well, one thing you can do is it reduces the effort that you need to set up this software infrastructure. So all of this kind of introductory stuff, things like the module environments, or even software specific things, like if you want to do a training course in GROMACS or TensorFlow or OpenFOAM or whatever software you might need, this is a space that we can help you out a lot with. The other thing that it does, it gives you a level of independence from the underlying system to an extent, right? So you still have to deal with the job submission system or whatever on a local system, whether it's Slurm or PBS or whatever it might be. There are some things that still have to come from the system, but all of that software level, all of the scientific software that people need to use, that could potentially come from EESSI. And the other thing that it really helps with is it makes it easy to transition from between systems, right? So whether that's a new system or new hardware, the view that the end user gets is the same across all these systems, even though they will be using new hardware on those systems. So that's also an interesting aspect. And on top of that, there are ways you can use EESSI as a base to provide additional software. So if we don't have what you need, you can actually use EESSI as a base and build on top of it. You can extend EESSI quite easily. What I just mentioned as well is that, there are a lot of tools out there right now that make setting up, for example, a Slurm cluster in the cloud is quite easy. There's a number of tools we use internally in EESSI. We use cluster in the cloud. I also contribute to Magic Castle, which is a very good one for training purposes. And in both of those tools, EESSI is a native option that is already available to you. There are also vendor-specific options that we've experimented with. So Cycle Cloud from Azure and Parallel Cluster from AWS. And one of the really good things is that the attendees, right? So when somebody comes to your training course, they can very easily set up exactly the same software environment later on their own systems, whether their own system means their own laptop, in a virtual machine, on a server they have access to, or even on an HPC system. It's possible for them to do this, to use the same environment. So in general, we've seen that EESSI can be used in infrastructure to support educational content delivery. But there's another aspect that I think is quite interesting, that it can also be leveraged to support content development. And I want to give a very specific example, which is related to HPC development best practices, right? So for me, over all these projects I've been involved with over the last 10 years or more, there's always this element of, when you talk about developing software for HPC systems, that people talk about giving courses on the best practices and how to approach that. And we do this, but even though we know that one of the most important things when you're developing a software project, or in terms of best practices, is to use continuous integration. But the reality is that continuous integration in the HPC context is extremely difficult. Okay, so you need very modern compilers, you need modern MPI runtimes, you need dependencies, specific versions of the dependencies built in a very specific way to run your software. And there are many restrictions that may come from whatever package you're developing for. And these need to be resolved somehow. And that's very difficult to do in general, especially when you talk about supporting multiple architectures. Because if you want to do it on multiple architectures, you need access to that spectrum of hardware. And that's not necessarily an easy thing to get. So the way EESSI can help support this is that it can potentially provide you with reproducible building and testing environments that will work on many different architectures. What we do currently right now in EESSI as regards access to hardware, and with the support of the cloud providers, is we use it ourselves as kind of a service, right? We provide a service, but it's something that we could extend to the community as well, with the support of cloud providers, whether that be commercial cloud providers or publicly funded ones. So I want to give a specific example of how this can be done. So we already have what's called a GitHub action on GitHub. So it basically means that you can use already EESSI in the CI environment that you can get on GitHub. So basically, it's a YAML format file. So an action in your workflow, and a CI workflow in GitHub is a YAML format file. You give some various things, right? You give the name of the software, for example, the name of the workflow, whatever you want to call it. You say on what kind of events you want it to operate on. So in this case, it's running on push events to the Git repository, or if somebody creates a pull request. And then you tell it what to do, right? So you tell it what operating system it's going to run on. So in this case, it's running on the latest version of Ubuntu that's available on GitHub. You tell it it needs to check out the repository. This is the standard one. But then I tell it I want to use the action that EESSI provides. And I tell it which version of our software stack you can. This is an optional one. You can tell it which version of the software stack you want to use. And then this will go away and do something in the background. And then at that point, then I can actually run the test that I'm really interested in. So in this case, it's a trivial test. I just want to load that GrowMax module and see what version it is, right? So I'm loading the GrowMax module without a version. I just want to see what version comes back, right? And this is that workflow. You probably find it hard to read this, but the point here is basically that whole process is running in a minute. So it takes a minute to get a fully capable environment that potentially has a mountain of software inside that you could leverage, right? So, and this is it takes 52 seconds to set up EESSI within the CI job. And the test is trivial, right? The test is just loading this GrowMax and then looking at the version, right? And so the test itself is trivial. So here I've used GrowMax, but you could easily conceive that here you could be talking about all your compilers, all your dependencies, everything you need to build your software, right? So this could all be available within a minute to you. And then you need to build up the cache for whatever you require, but it can all be done very quickly. So that's something I think is really interesting to look at as a way to provide a backbone for something like CI in the HPC space, or at least generating a course that can teach people about that. And that is all I wanted to cover. And there's a lot of links here, and we'll provide a link to the slides or a copy of the slides, so that if you want to follow all the links and everything. So we have mailing lists, we have documentation, and all our repositories in our GitHub. We have a Twitter account, the channel. We have monthly meetings, and so in our YouTube channel, we very recently had our first user meeting. So I think a couple of months ago, and so you can look at all the videos from there, which give you a really good overview of where we are at the moment. So that was a lot of talking, but I was wondering, we're exactly on time. So I was wondering if there's any questions.
Thank you, Al and Ken. Are there questions for either presenter? That was a very comprehensive overview, and I'm fascinated by the idea of using this for training, because I think that's been a very difficult thing to do on production systems, because most system administrators don't want to make reservations for large scale training kinds of opportunities. So this is a really interesting idea, I think.
Yeah, I think there's a lot of scope there for something like this, and it'll be interesting to see how far we manage to get in the next few years and what kind of examples we can show off.
Scott asked the question, are you seeing any adoption in the US?
Yeah, that's maybe the European part in the project name talking. So this is not really specific to Europe at all, except for maybe the funding that we now have is the Euro HPC project. But other than that, this is worldwide accessible. Actually, one of our mirror servers is running in Azure, and that one is running somewhere in a data center in the US East, I think. So seeing adoption, that's a good question, because we generally don't know who's using this. So it's freely available. It's just a web server. And just like a website, unless you're starting to track your users, which we don't want to do, you don't really know who's using it. Yeah, so we do have some good connections with some of the Microsoft Azure HPC team in the US, for example. They've been very, very helpful, very responsive. We have monthly meetings with them to show what we're working on currently, where we're stuck currently. They're helping us to set up a Slurm cluster in Azure with InfiniBand capabilities, for example, for testing purposes. So to that extent, yeah, I don't know if you can call that adoption, but there's definitely interest there as well.
Excellent. Any other questions?
Yeah, the tracking usage, so that's one that comes back more often. So as far as we know, CVMFS currently doesn't have a direct way of tracking usage, because you're not always talking to the central server. You may be talking to one of these mirror servers, and each site can actually stand up their own mirror server and not tell anyone. So if they're accessing the EESSI repository through that way, it's very difficult to detect. So yeah, just by the nature of how CVMFS works, it's quite difficult to get at least accurate usage results. There's proxies though, so we can check bandwidth usage of the mirror servers. We can check how many different IPs are talking to the mirror server. So there's things we can do, but having very reliable user statistics will be very difficult.
Okay. Well, thank you again for the presentation, and I will be making the recording of this and putting it on the YouTube channel for the chapter, and I assume you'll want to link to that to put on your own YouTube channel. So thanks again. It was very interesting and presentation, and I some very interesting ideas, and I wish you the best to make this work with even more scattered types of systems and software. So with that, we'll end today's presentation, and everyone have a wonderful day. Thank you.